In our discussion, we will look at a closed loop system. You can stick around with this video towards the end so you can fully understand what is a closed loop system. I will also give you some example for you to firstly understand how does a closed loop system operate. If you want to know open loop system, you can check our previous video and also the introduction to the control system. Why the control system is important. After you completely watch all the video, I believe you should be able to differentiate the type of control systems that we have and how they operate. With the simple example I will be giving in this video, it is important you stick with this video to the end and you will fully get what is needed to understand the concept behind a closed loop control system. Unlike the open loop system, we have in a closed loop many block diagrams that can represent the feedback and the feed forward of a system. In a closed loop, we now have the feed forward plus the feedback. In open loop, we understand that there are only feed forward system where there are no feedback. With the increase in the block diagram in the feedback, it is important that you understand the block diagram representation. And this is the first step to understand how the closed loop is represented using the block diagram. And we will start with the arithmetic, such as the addition. What do we mean by the addition? We have a block diagram which is given like this, which is called a comparator. And when we have a set of signal, for example, signal X and signal Y, you will now have plus and plus. That means the output, which we call Z, will now be equals to X plus Y. That means the signal X is now headed with the signal Y to produce the output X. And this can be seen in the Kirchhoff current law, where it is defined as the sum of current entering a node must be equals to the sum of current leaving the node, or the sum of current at a node will be equivalent to 0. If we have I1, I2, and I3, I4, it can be represented mathematically as I2 plus I1 is equals to I4 plus I3. This is the KCL for an electrical circuit. Now we will look at the subtraction. The subtraction, we can have Z, X, and Y. We can have plus and minus. Now Z is equivalent to X minus Y. And this is mostly found in a closed loop system. All these block diagrams are important and useful. They normally describe the properties of elements and the system. Another one is called the scalar multiplication. In a scalar multiplication, the block diagram is written as we have X and we have Z, then this scalar is a constant. Now the output Z is equivalent to Kx. The important thing to remember is in such block diagram, the output is equals to the gain of the system, which is a constant, multiplied by the input. When you are analyzing a control system, anything that is connected between the input and the output must be analyzed in such a way where the gain can be from an element of a control system. It can be a controller, or it can be a process, or it can be the feedback gain of the system. Therefore, when you want to take the output of this particular element, the gain of the system must multiply with the input of this particular element to produce the response. Another one is called the variable multiplication. With the term multiplication, we know that for a system, we should have input x and input y will produce output z. Since it is a variable multiplication, that means input x represents a variable and input y is also a variable. And previously we talked about variable, which is nothing but the quantity itself. And quantity is anything that can be measured. So the variable can be a temperature, it can be a voltage, it can be the weight, it can be the length, volume, and etc. And this variable can be represented as A, B, C, D, all the way to X, Y, and Z. When we talk about the variable representation, we normally use the letters. And we all know that the letters will contain the numbers. In most of our discussion, we will be able to use a variable which qualify for a value. And this value will have a unit that will correspond to whichever variable we are dealing with. If we are dealing with temperature, we all know that the unit will be in degrees Celsius. For the voltage, we can say V is the unit or the volts that represent a magnitude of a voltage. And in this variable multiplication, we can see that Z is now equivalent to X times the value of Y. And this represents variable multiplication. Another one, which is mostly used in mathematics, it is called the function. So what is really a function? A function normally can be represented as function of some variable. If we have x as an input and z is the output, now the function is normally written as f of x will be equals to z. So z will be the function of the x. Depending on whatever function that is embedded in this system, the response of the system becomes the function. We have different function in mathematics, and if such function is applied to the input, then it will produce the response, which is the z. And this can lead us to a good example of a function which we know as the integration. The integration is now a function. Imagine if we have the block diagram which now represent the integrator. So we have z as the output to this function and we have x as an input. Now we can say the z is equals to the integration of x dt. The integrator is now the function of this particular system. When we say z is equals to f of x, now it is equals to the integration of x dt. So we will explain more on integration in our mathematics video. And if you want to learn integration into more detail and what it does to a input variable to a system, you can check our videos to get more idea about how the integration works. And finally, we will look at the differentiation. A differentiation is also a function, and this function is represented as d on dt. When we have input x which produce output y, the system now is a differentiator. So we can say the system is a differentiator, and differentiator is nothing but a second. Now we can have let's say if this one is z, since we are dealing with z as the output, we can now say z is equivalent to d on dt of x. And now this is our function. Now if we say the output z is equals to the function of x, it is now equals to d on dt x. So we are now differentiating the input to produce the output. And we can see that those block diagrams plays an important role in control system. So we have the system, and those system can be represented by the block diagram. And we have the output of the system, now let's say y, and we have the input to the system x. So y is always equals to the system gain of this block diagram. We can say beta is equals to beta times the input x. This can be a very simple way of representing a system. Or we can say the output y is equals to the function of the x, and the function of this x is the operation that is done on the input signal x. Now we can start by looking at the closed loop system. We'll start with the thermostat. So what is a thermostat? So a thermostat can be a closed loop system. The thermostat is defined as a regulating device that regulates the temperature. When we say regulate the temperature, that means it is now able to sense the temperature of a physical system and perform some kind of action or regulatory process so that to achieve temperature stability, or we can say maintain the temperature. And when you have heating devices and the cooling devices, we always have the thermostat inbuilt to those devices. When we want to eat a particular application, we always want to regulate the heat at a certain degree. Or if we are cooling something, we will use a cooling system that will have a set point. And this set point can be regarded as a threshold. We don't want to cool below this particular threshold. Similar for the heating, we can heat to a point where we cannot heat more than. In that case, we now regulate the temperature, and it can be found in many devices and many applications. And it is a good example of a closed loop system. Now we can look at the block diagram of a system that have a thermostat. Now we will look at a temperature control system. And this can be the simplest of all other control system having a closed loop. In a temperature control system, we normally have the input and the controller, and now we can have the controller. This is for a closed loop system. And we can have the actuator, and we can have the process, and we have now the output and the input. And since it is a closed loop, we now have the feedback, and the feedback is now connected to the comparator. So this is the closed loop block diagram. And with the closed loop in mind, we can now draw the system itself, and we can have the regulator which perform on or off operation, and we can discuss the heating system, we can say a room, or the control temperature. This can be the room, and we have the output, and we can have a temperature sensor as our feedback element, which is now connected to the output. The output, we can say the actual temperature, and the input, we can say the desired temperature, and we can say plus or minus. Later I will explain the plus and minus, which means it is a negative feedback. And why do we have negative feedback and positive feedback in a closed loop system? I will explain later on in the video when we look at the transfer function of the closed loop system. And we can put the dot here to represent the thermostat, because previously we said the thermostat is responsible for regulating the temperature. Therefore, we have the regulator, which represents the thermostat, and it has the desired temperature with the actual temperature. And if you like our video, you can click the subscribe button and share with your friends in order for them to know what is a control system and how they can apply control system in real life application. Now I want you to remember that this is an electrical circuit. When we say electrical circuit, it mostly deals with voltage and the current. And this voltage and current, they have a relationship with the temperature. And we can state the relationship of a temperature with respect to the voltage. And this temperature have a unit of degree Celsius and the voltage have a unit of volts. They have a relationship. And for the temperature sensor, how can you define a sensor? Well, a sensor is an electrical device which convert signal from the environment, such as temperature, the speed, into electrical signal. And we can say the sensor is nothing but can be in the form of a resistive sensor, a capacitive sensor, inductive sensor, and so on. And those sensors, as I have mentioned, they normally convert the real parameters from the environment, such as heat, such as speed, such as weight, and it converts to electrical signal. And this electrical signal will now be able to be computed in an electrical circuit, such as the temperature control system. And this is important for you to understand, because this circuit does not deal with temperature itself. However, it is dealing with the electrical parameters such as voltage, current, the frequency, like what we have mentioned in our previous video about the relationship between those quantities, such as the temperature and the voltage. Now, if you understand this, we will now proceed to understand this control system of the temperature. From the desired temperature, we normally have a reference signal that correspond to a set of desired electrical parameters such as the voltage. If you can find this thermostat example in a fridge, if you want to set the temperature, you have a knob which is connected to a certain level, such as if you want to select 0 degrees Celsius, for example, 10 degrees Celsius, 20 degrees Celsius, and 30 degrees Celsius. If you want to change the knob to 10 degrees Celsius, then you will have to turn this knob to align with the 10 degrees Celsius. And this can be regarded as a voltage variable source or a voltage divider. However, when we are dealing with the heating element, Unlike in the fridge, we normally control the coldness inside the fridge. But in this case, for a heating element, if we are working in a furnace and we require a certain amount of heat to melt a particular material, now we can use this example to illustrate. So we can give the relationship. Let's see, we have for each of these the 30 degrees Celsius, which is the maximum heat this heating system can be able to produce. When we give the relationship, we can say 0 degrees Celsius example is equals to 0 volts. And if we say 10 degrees Celsius, it is equivalent to example 10 millivolts. For 20 degrees Celsius, it is equivalent to 20 millivolts, and 30 degrees Celsius will be equivalent to 30 millivolts. How can we get the millivolts? Now, if you look at this knob, the knob is designed in such a way as a voltage divider. So we can have a voltage divider circuit, and we define a voltage divider circuit as the output of the voltage divider circuit will be equals to the desired or the reference temperature. That means this is variable. And if we have, for example, positive 5 volts and we have 1000 ohms here, and then we can be able to regulate the type of resistor that we use in this case. Example, if we want the V out to have 30 millivolts at the output, what type of variable resistor can we choose? Maybe I need to explain step by step so you can be able to understand. Now, if we say from the rule, we have the V out equation of the voltage divider, we have R2 over R1 plus R2 multiplied by the V in. So we have the parameters such as R1 and R2 is variable. We have the input voltage and we have the range of output voltage that needs to be measured. And the unknown is the R2. So we can look at the maximum value, which is 30 millivolts, and we can compute. By solving this equation, by inserting the values, we can now find R2, which should be equals to 64 ohms. And the range is from 1 ohms to 64 ohms. And this is our variable resistor that we can be able to use to set the equivalent between the temperature and the voltage. When we tune the knob to the maximum, that means that the resistor R2 will be equals to 64 ohms, which is equivalent to 30 degrees Celsius, and it is equivalent to the V out of 30 millivolts. And if we want to get 20 degrees Celsius, how can we compute with this equation? Then we can say V out is equals to 20 millivolts, which is equivalent to 20 degrees Celsius. And what will be the resistance? The resistance will now be equivalent to 42 ohms. So that means when we increase the knob, we are increasing the resistance, and it will provide the equivalent voltage to control this heating circuit. And also from this temperature sensor, the temperature sensor will have the relationship which is now similar to what we have discussed here. If the temperature is 30 degrees Celsius, the output will be 30 millivolts. And when we have 10 degrees Celsius, we can have 10 millivolts. And now we will compute with respect to the comparator. The output of the comparator to the input of this regulator is known as the error signal. And this error signal is now responsible for enabling the regulator to turn off or turn on. When we say turn on, that means the heater is on. When we say turn off, then the heater is off. And the turn on and turn off is now depend on the error signal from the comparator. So I will explain what will happen. Initially, when we say the temperature is around 20 degrees Celsius, that is closer to the room temperature. So we want the heating element to have 30 degrees Celsius. Therefore, we can say the input or the reference will be 30 degrees Celsius. And we all know that the voltage applied to the positive end of the comparator is 30 millivolts. And from this output of the system, we have 20 millivolts. So we have 20 millivolts, which is coming out from the temperature sensor. Now we can say the error signal is equals to the reference minus the sensor value. We can say reference value and the sensor value. And this value is in terms of the voltage. And we should have 30 millivolts minus 20 millivolts. So we have a positive 10 millivolts error signal at the output of the comparator. Now it will turn the regulator on. In that case, this regulator will perform the heating. It will heat the element while we keep this reference constant. That means this will be our position of the knob. And this will increase to 21 degrees Celsius all the way to 30 degrees Celsius. Now when the actual temperature is 30 degrees Celsius, we will now have 30 millivolts at the output of the sensor. Now what will be our new value? We will have 30 millivolts minus 30 millivolts, which will now give us 0 volts. Now when this one is 0 volts, that means this regulator will switch off. When it switches off, that means no heating will be performed. So this is our reference temperature, the desired temperature. And this system will be available for the constant period of 30 degrees Celsius, and it will monitor the output. And this will keep on heating, and to a point where if it is decreasing, if the heat is decreased to, for example, 25 degrees Celsius, and now we will have 25 millivolts at the output. When it is 25 millivolts, we now have a difference of 0.5 millivolts. Now towards the positive, when we have error towards the positive, now it will switch the regulator on to perform the heating. So the underlying of this system, we can see that it performs some automation. We don't need someone to measure the temperature every now and then to turn on and off the heating element. So from this idea, we can see that automation comes into play, and we can see that precision is also required, and external disturbance and the reliability of a system. All of this plays an important role in this particular heating circuit. So we can say that by looking at this figure and the explanation, we can say the reference temperature must always be equal to the actual temperature. So that's how this particular system will operate. So every time when we turn the knob to control the particular temperature between the input and the output, the system will react in such a way that it will maintain that the reference temperature or the temperature we want must be kept constant at the output. And this can be seen with respect to the air conditioning system. They all behave in the same manner. And I believe with this explanation, you can fully understand what is normally happen in such a closed loop system. When we want to have automation and we talk about the precision, we want the output to be the same as the input or the desired input that we want, then we normally choose a closed loop control system. As a designer, you would later want to design a system, and with this basic understanding of how the system operates will help you to design a reliable circuit that is more precise and it is more reliable for the user. Because whatever system you are developing, the people will be able to benefit from it. So choosing a reliable system with more precision will be our target. We will also discuss the relationship between the input and the output, with respect to the transfer function. And by then, we can substitute the values and how we can create a system that is more stable. And by applying the feedback, we can prove that any closed loop system with a feedback will produce a stable system compared to the open loop control system. And if you have any question, you can comment down below and we can discuss more about the closed loop control system.